Our next topic is experimental kinetics, in particular integrated rate laws and half-lives. The idea here is that each order of reaction has its own concentration of reactant versus time behavior, and so we can use the concentration versus time plot to figure out what the order of the reaction is. The idea here is that we're always considering a reaction that's like some generic reactant A goes to products. And the idea is that depending on what the order of this reaction is, we have a different differential rate law. So zero order rate is just, negative change in concentration of A over T, right? That's the definition of the rate. And then if it's zeroth order, then it's K times A to the zero. That'll give us this concentration versus time plot. For first order, again, we'll get a different concentration versus time. Second order, a different concentration still. We'll see how we can use this behavior to figure out what the order of the reaction is. The best way I think to look at this is to fill out this table. This is something I definitely encourage you to write out yourself in your notes. As usual in 120, you're going to get the equations on the quizzes and exams, but you do need to be able to know which equation goes with which order. So first, if it's a zeroth order reaction, then we have rate is equal to K times, if we use A as that generic reaction, it'll be Ka to the 0. Again, anything to the 0 just cancels out there. So just K. Then for first order, of course, our rate law is just K equal to K, A to the first. Again, anything the first power is itself, so just Ka. Second order, Ka squared. Next, we'll see what happens for the actual concentration versus time behavior as we'll fill that out. Our first one we'll look at is first order. I think that's more useful than starting at zeroth order because this is the most common case. First order, we have, A goes to products. We have that differential rate law. It turns out that if you use calculus, you can see what this looks like. Using some calculus, which we don't have to do in Chemistry 120, but calculus will get you to this final answer, that the concentration has this behavior ln of A is equal to ln of A naught minus KT. This is an example, like radioactive decay is an example of this. Those are always first order processes. And again, anything in general where just the thing is falling apart on its own, so decomposition is often a first order process. We have this other form of the integrated rate law as well. Basically just using our rules for logarithm, we can go from this form to this form where it's a ratio form. This is nice because now when I have the ratio here, what's interesting is that it doesn't matter what my A naught is. If I just set my A naught to like 100%, it's, and let's say A then is like 10% remaining. Even if I don't know the actual units of the concentration there, if I know that I started with 100% and I ended with 10%, I can use this integrated rate law to figure out how much time that takes or to figure out what my rate constant is. Very, very powerful for things like radioactive carbon dating and things like that, where we might not know the initial concentration, but we just know we have 10% of the carbon-14 left. Okay, that's just the meanings of these equations for integrated rate laws. One thing to note here, again, is that there is a key relationship between the integrated rate law here and the differential rate law here. So since it's a first order process, rate is equal to Ka, so this is a first order direct linear relationship. So the higher the rate, the higher that A is in a linear way. Remember that the rate is negative delta A over T, so that's the slope of my A versus T graph, or the negative slope there. So on this graph I can see my rate started out very fast. Then when I decrease the amount of A, my rate slows down, and here my rate slows down even more. And that's why this graph here gives us information about the rate law, is because of this sort of calculus relationship between those. In general, whenever we have these, we want to go to a straight line. So we want to take whatever graph here, in this case this nice curve, and we want to plot it in a way to make a straight line. So if we look at this equation, we have ln of A over here, ln of A naught minus KT. So if we plot t on the x-axis, and if we plotted a on the y-axis, it would not be linear. That was that nonlinear graph that we show here. But if we plot ln of a, according to this equation, ln of a should be linear. When we line up those equations, just like we did for, say, the Arrhenius equation, ln of a is our y variable, t is our x variable, so that leaves the stuff multiplied by the x variable. That's always our slope. So slope is equal to negative k, the rate constant. And again, we can see the y-intercept here is going to be ln of a naught. So that's what this shows here. This isn't really something you have to memorize, because if you just know how to compare the equation to the y equals mx plus b line, you can just understand from the equation which you're given what the slope and what the y-intercept are. Okay, so we can then continue to fill out this integrated rate law table. For first order, it's these three equations describe the integrated rate law: the concentration versus time behavior, the sort of normal linear form, which is designed to line up with that y equals mx plus b, the ratio form, and in this case, if we take e to the power of both sides, we also get this form, just sort of an exponential form. If you remember that relationship between exponents and ln, that those are sort of inverse operations of each other, you should be able to recognize that this is also a first order integrated rate law. Our linear plot, because this is the integrated rate law, is ln of a versus t, so that's our characteristic of it being a first order reaction. Next, let's look at a second order process. So in this case, an example here would be if two things sort of smashed into each other. So like two molecules of HI colliding to make H2 and I2. That happens to be second order then in the reactant HI. We have our differential rate law over here. Again, because it's two things colliding, it's a second order reaction, a to the a squared here. As usual, again, you're not going to have to do the calculus, but through calculus, we get to this overall integrated rate law. 1 over a is kt plus 1 over a naught. Now this relates the concentration of a reactant A versus time to the time t and the initial concentration A naught. So what was A at the start of the experiment? We can then look at that over here on our reaction A versus T and rate versus A graphs. So again, because it's a squared relationship, this graph looks like a parabola. So the rate is slow, faster, and then much faster. Doubling A leads to a 4x increase in concentration. Again, we can see that over here, that the slope here starts very, very steep, but it flattens out really dramatically over time, again, because of that squared relationship. Now, again, since this is nonlinear, what's the graph that's going to give us a straight line? Well, since it's 1 over a here, if we plot 1 over a on the y-axis, we're going to get a straight line with the slope of k, because we can see that k is in that slope position, and we can see that the y-intercept is going to be 1 over a naught. So that's the y-intercept on this graph, and that's how you can recognize a second order reaction. Again, we'll start to use these equations later. The only new variables here are, again, a concentration of a at some time. A naught is the concentration of a at the initial time. Again, we've used k, and then small t is time, whereas we use capital T for temperature. Our last example here is a 0th order reaction. In that case, we have rate is equal to k is negative delta A over delta T. So what that looks like here is that the rate is just a constant number. So I'm drawing this a little bit more realistically. Eventually the rate does have to go to 0 if A has a concentration of 0, but at any reasonable concentration, the rate is basically constant. An example would be, say, this decomposition of N2O on platinum. So in this case, we have a bunch of N2O, enough to completely cover the surface. And so since the surface is basically always covered, no matter how much N2O I have, any increase in N2O doesn't increase my rate at all. That's the idea of a 0 order process, that it's only this reaction only occurs on on the surface. So while the surface is covered, change in concentration doesn't affect the rate. Again, we use our calculus approach. In this case, there isn't really any calculus needed. It's a constant rate of reaction, so that's just the same amount of A used up every second or minute until the reaction is over. The final equation that we get is here, so the concentration of A at some time is equal to negative K times the amount of time plus the initial amount. So the concentration just keeps going out down by 0.1 molar per second, say, every second until we use up all of our A. What that looks like then on our graph is just a straight graph of A versus time. So we start at a concentration A naught, and since the slope is the rate, a constant rate means a constant slope on that A versus T graph, and A versus T is our linear plot for a 0th order reaction. Again, that can't continue forever, but for our purposes, eventually it'll flatten out. But for a long time, it will be pretty much flat, straight linear. So here's our key summary table again. You will always get all of these equations, but again, you should line up what integrated rate law goes to what order. So again, for 0th order, the linear plot is A versus T. For 1st order, ln. For 2nd order, 1 over A versus T. If you memorize that little bit, then you can, whenever you look at your equation sheet, see, okay, the thing that has A and T in it, that's a 0th order integrated rate law. Anything that has ln of A and T in it, like this, ln of A and T, or again, ln, or again, since e to the power of is the inverse of ln, this exponential one is also sort of the logarithm exponential type equation. Those are all ln of A versus T integrated rate laws. Then for 2nd order, the one with 1 over A in it is the 2nd order integrated rate law. So a little bit to memorize, but really only this key fact. The other thing you're going to need to be able to do is use the graph and use its slope and intercept to figure out things about the reaction. Again, we wrote down what those sort of key answers were, but you don't really need to memorize anything. If you just look at the integrated rate law, let's use 0th order as an example, you can see how the parameters from the linear plot or linear fit give you information about the reaction. Remember, the equation of a line is y equals mx plus b. And so if I look at that equation of the line, I can read off, okay, my plot is A versus T. So I've got A as my y variable. I've got T as my x variable. And then if I look at what's in the position of slope, it's negative K is equal to my slope. In the same way, the B position or y-intercept position is equal to A naught. So sometimes, some people like to write this out explicitly, and you're free to do that if you want, to write out that, on this graph, the slope and intercept, we have like negative K is equal to the slope, and A naught is equal to, let's say, B, the y-intercept. I've sort of taken that off this summary information just because I think you can always read it off yourself. We'll see that it is pretty much always the case that the slope is equal to K, either with a plus or negative sign on it, so we always get the slope from we always get K from the slope. The y-intercept always gives us information about the initial concentration. In this case, it's just the y-intercept is equal to A naught, but we can see what that looks like for the other couple of rate laws too. If I go to the ln of A, this one here, and I do that same thing, lining up y equals mx plus b, my y is ln of A, my x is t. So that means the thing that's added then is ln of A, that's my b, and the slope position is still negative K there. Again, if I look at 2nd order, 1 over A is in my y position, t is my x, so that leaves K is my slope, right? The thing multiplied by the x variable is always equal to the slope. And 1 over A is my y-intercept, or b. So again, feel free to write those out if you want, but again, as we keep doing this, you should be able to sort of practice just looking at the equation and seeing what is in what position. Here's our first exercise, looking at this data, determine the order. rate constant, units, and C here, concentration after that amount of time. See what of that you can figure out on your own, and then I'll show the solution. First, what is the order of the reaction, and explain. So from that, it comes down to which graph is linear. So concentration versus time is here. That's not linear. ln of concentration versus time, also not linear. It turns out 1 over concentration versus time is our linear plot in this case. That is something you sort of need to memorize, is which linear plot goes with which order. It turns out to be second order. So 1 over A versus T is linear, and that means it's a second order reaction. Whichever the linear plot is tells you the order. Next, if the linear fit of the data returned this equation, so that's the best fit line on this plot, has this parameters, what is the value of the rate constant and the initial concentration of the reactants, including units? Okay, so value of the rate constant, remember the rate constant is K, and initial concentration of the reactant. So that's going to be, again, in our notation, A naught. Those are the things we're trying to find. We can find that by looking at that linear equation and comparing it to the best fit line. So we have our normal, like y equals mx plus b, and I'll write that out. Y is equal to 0.00350, x plus 2.081. We compare that to the equation of our model, which is 1 over a. So we look at the equation sheet, which says 1 over a is equal to kt plus 1 over a naught. And again, the power of this approach is that now we just line up things that are the same in the same position. So 1 over a is our y variable, right? We can see that there. The x variable is the time t. And now everything else needs to match up as well. So k, in this case it's just k, there's no negative. K is equal to 0.00350. And again, sort of in the same way, 1 over a is equal to 2.081. Now, we do need to worry about units. Again, remember how the units work here. Whenever I have a graph, the slope is rise over run. And so it has units that are the y unit over the x unit. So in this case, my y-axis has units of molar to the minus first. My x-axis has units of time. So my slope there is actually 0.00350. My y unit is molar to the minus 1. My x unit is seconds, so y unit, molar to the minus 1, divided by x unit, which is seconds. So molar to the minus 1 over seconds. And that is, again, according to this matching we just did, that is equal to my rate constant k that I wanted to solve for. So that's sort of the answer. Again, maybe a cleaner way of writing the unit there would be molar to the minus 1, seconds to the minus 1. Next, what about the initial concentration? For that, I can use this relationship. 2.081 is equal to 1 over a naught. Again, from just lining up these two positions in the equation. 2.081 though does also come with units. Remember that what the y-intercept means is it's the value of the y-axis when I cross 0. So because the y-axis has units of molar to the minus first, this 2.081 has the same units. Again, y-intercept is just equal to sort of the y unit. Again, the units on those. So 2.081 molar to the minus first. Now when I solve, that will give me the proper unit. So this is similar to when we had like 1 over wavelength, right? The easiest way to deal with this is just to take 1 over both sides, doing that inverse operation. When I do that, I get a naught on the left-hand side, and that's going to be equal to 1 over 2.081 molar to the minus 1. is equal to, no, oh, I'm in scientific notation here, so 4.8 times 10 to the minus 1, or 0.481. And again, since molar to the minus 1 was on the bottom, we're in molar here, is equal to A naught. So that's the answer there. In this case, we didn't have to go through all that math. You could have actually just read it off of the table. We were given the data table, so we could have avoided ourselves doing some math and just said A naught is equal to 0.480 here, because it's right there in the table. But again, sometimes you'll need to be able to use the graph to figure out the value of A naught, which we can easily do there. Okay, so for part C, concentration of 1,3-pentadiene after 8,500 seconds, it gives us the hint to use the equation of the line. That's often the easiest way to do this type of problem. So if we do that, all we're doing here is we're going to plug into y is equal to 0.00350. We do have proper units on it, but I'm just going to leave them off for now for the sake of writing. 8,500 seconds, that's our value of the x-axis. So since I have my time here, I can plug that in for x. Time is equal to x. So I plug in 8,500 here. The units here need to match the units here on the graph. And that will give me my value of y. That gives me a value of y of 31.83. And again, remember my y-axis is molar to the minus 1. That should make sense. Here we were at about 17 after 4,000 seconds. So again, it's linear. It'll basically double. Yeah, get close to 34 after 8,500 seconds. Sure, that seems reasonable. Now, my y value is not equal to my concentration, but according to the graph, it's equal to 1 over my concentration. So this is equal to 1 over concentration. And then I do that same inverse transformation I did before. Just take 1 over both sides, and I'm going to get A is equal to 1 over 31.83, which is equal to 0.0314 molar. Always make sure you're using proper units. What you can maybe also double check based on your concentration versus time graph. Concentration versus time after 4,000 or 5,000. 5,000 seconds was 0.0510. So we're at 0.0310 after 3,000 more seconds. That's plausible, right? If we got a concentration here that was like 0.1, that would be completely ridiculous because it was 0.1 a while ago. So, because often if you're going to make a mistake here, it's going to be off by a huge amount just because of a calculator or math error or something like that. So you can check from like the data or the A versus T graph whether things are plausible. When we do half-lives in a minute, half-lives give you another way to get a order of magnitude or rule of thumb as to whether you're on the right track here. So this is sort of a general approach for figuring out the order of the reaction, concentration versus time, L-line of concentration versus time, and 1 over concentration versus time. Once you have those graphs, find the linear one and use that to figure out the parameters of the reaction. Okay, so at this point we've now have these integrated rate laws. You can actually do a ton of problems with these because these will tell you exactly how concentration varies with time for any of these type of unimolecular chemical reactions. So you can see how a drug is getting metabolized over time in your body, or how a radioactive element is decaying over time, letting you carbon date things. All sorts of things you can do just by knowing each of these equations and then plugging in and using it for various purposes. Right, again, there might be a certain level of acetaminophen or something like that below which it's no longer effective. You can see how many hours it will take to reach that point and therefore when you need to take your next dose. The next thing we want to do then is look at half-life. So that's a new parameter that will give us information about the rate constant, the concentration versus time behavior, and even could be a way to let you figure out the order of a reaction. The definition of half-life is the time required for a reactant to reach half of its original concentration. So we denote it T under like subscript 1/2. And each order of reaction has its own formula for half-life. You could calculate or derive the half-life by just plugging into the integrated rate law to see when it reaches half the original concentration. So here's what the equations actually look like. For the 0th order, we have an equation that looks like this. A naught over 2k is equal to T 1/2. So just to explain what that means is, again, let's say we have an initial reaction here where A naught is equal to 1 molar. And again, I'll just pick a K that's, say, 0.1. In this case, molar per minute would be a right unit for a 0th order K. What that means then is I can see what happens to the concentration versus time in terms of the half-life. So let's see what A looks like at different times. Sorry, I got that the wrong way. Time and the amount of A. So initially we had 1 molar. Now what the half-life for 0th order is here is I go A naught over 2 times K. So this first half-life would be 1 molar over 2 times 0.1 molar per minute. And if I look at that equation, I get 1 divided by, this is 0.2 when I multiply that out, which is equal to 5 minutes there when I plug in for the half-life. So what that means is that at 5 minutes, my concentration of A would have cut in half to exactly 0.5 molar. Now, the next half-life, what's going to happen? Well, for the next half-life, I still have the same K, and this 2K is the same, but now my initial A naught for the next half-life is only 0.5. So now for the next half-life, I'll plug in 0.5 up there, and you can see what's going to happen. 0.5 divided by 0.2 is only going to be 2.5 minutes. Again, that's not a surprise, because if I look at how this works, when A cuts in half, T 1/2 will cut in half, because it's a direct relationship here. So now at 7.5 minutes, 2.5 extra minutes, my concentration of A goes to 0.25. At 8.75 minutes, my concentration of A would be 0.125, and so on and so forth. Each half-life gets shorter and shorter as I keep cutting A by a factor of 2. In contrast, for a first-order reaction, we have this half-life equation. So let's say I have that exact same initial conditions, and my K here with units will be 0.1 per minute, or minute to the minus 1. For the first half-life, I'm going to look at 0.693 over 0.1 minute to the minus 1. That's going to give me 6.93 minutes. I'll approximate that to 2 significant figures, so 6.9 minutes. My concentration of A, again, cut in half. That's what half-life means. Now what's interesting about this is there's no dependence on concentration here. Every half-life is going to take 6.9 minutes. So if I add 6.9 more minutes, that's going to get me to 13.8 minutes. And at that point, I'm going to be at 0.25 molar. Again, what if I add another half-life, 0.125? That's going to be 20.7 molar. Not 20.7 minutes. So every single time I add another 6.9 minutes, I cut in half again and again. That's the only order where that's true, where the half-life stay constant as I keep going. And again, that's because it's not in that equation. What if I look at a second order half-life? So in this case, if I start with 0.1 per molar per minute here, and again, the same 1 molar initial concentration, what do I get? Well, I'll plug into the half-life equation. K is going to be divided by K is 0.1 molar times minute, and then A is 1 molar. So that will just work out to 1 over 0.1, or 10 minutes. So at 10 minutes, I'm going to reach a concentration of 0.5 molar. But now look at what happens to half-lives here. What I'm going to plug in for my next concentration of A is not 1, but 0.5. So now I'm going to be at a concentration of 0.5 molar. When I have a concentration of 0.5 molar, what's going to happen? Well, this is an inverse relationship. The lower A gets, the longer the half-life gets. So A cut in half, so the half-life doubles. This is now 20 minutes for the next half-life. So I have to wait till 10 plus 20 more minutes is 30 minutes. I'll reach a concentration of 0.25 because this half-life now was 20 minutes. My next half-life, when I reduce the concentration to 0.25, will be doubled again. So it will now be a 40-minute half-life. So 30 plus 40, it'll take 70 minutes, and I'll get to a concentration of 0.125. So in this case, I'm looking at 3 reactions where the initial rate was exactly the same because it was a 1 molar concentration. So these all started at the same rate, but since the 0th order, the reaction never got any slower. You can see that the first half-life was a little faster, 5 versus 6.9 versus 10 minutes, but then the extra half-lives get much, much faster. So here it only takes us 8.75 minutes to get down to 0.125 molar. Here it takes 21 minutes to get there. Here it took us 70 minutes, much, much, much longer as those half-lives keep stretching out. So with that, we've really done all of the content for this set of slides. Now there are a lot of equations, a lot of different ways to use them, so this is one we're definitely doing. A lot of practice problems will help, and just, being familiar with the algebra. Again, we're going to have to solve natural logarithms and exponentials, so remembering that math content, that those are inverse operations, is going to be really important. We'll do a lot of practice here. Again, to make sense of the equations, remember that what you need to memorize is this. A versus T is 0th order, ln of A versus T is 1st order, 1 over A versus T is 2nd order. Now, again, that also goes along with these half-life equations. You'll get all these equations on the quizzes and exams. And again, if you look at them carefully, you can see that the half-life that has A in it, A on top here, that is the 0th order half. The 1st order is the one that is ln of A versus T, so it's the one that has ln in it, ln of 2 or 0.693. That's also a constant half-life, something you might want to really remember because it does come up quite a bit. 1 over A versus T is 2nd order, so the half-life equation that has 1 over A in it is the 2nd order half-life. Now, another thing that comes out of this is the units on K. There are so many ways to get the units on K. You can remember it right from the rate law. That's a good way to get it. Another really good one is from the slope of the graph. So if I think about this, remember that the linear plot here is the one thing I need to memorize. And for all these, it turns out that the slope of the graph, and when I take the absolute value of it, I just need to make it positive. That's going to be equal to my rate constant. So that's true for all of these. Again, K is a rate constant. It's always positive. So whatever the slope is, if I just make it a positive number, that will be equal to my rate constant. Now the slope is equal to K. And so remember, since then the units there are going to be the Y unit over the X unit. So if I look at this, Y, this is always written as Y versus X. So the units on K are going to be the units on A divided by T, which is molar per second. For this 1st order one, the units on K are the units of ln of A divided by the units of time. ln is unitless, so that will give us 1 over seconds, or 1 over time, for my units here. Now 1 over A, the units of that are 1 over molar, divided by seconds, gives me a unit here of molar to the minus 1, seconds to the minus 1. So again, this is something you could sort of try to remember how the units on K work. 0th order molar per second, 1st order 1 over second, 2nd order 1 over molar times seconds. But it does also just come right out of that one thing you need to memorize. Because K is equal to the slope, if I look at the slope here, Y over X, I get the units on my K for free. Okay, so this is just that same summary information in more detail. We've got these integrated rate laws, again, concentration versus time. And by transforming those graphs, we get this nice linear plot, and can then also have the characteristic half-life for each of these. Here's our next example, 3 different parts. Take a minute to try to do these, and then I'll show the solution. Okay, so for part A, usually the hardest part about these is finding the order of the reactions. So in this case, it gives us to it. That's valuable information that it's first order. It gives us the rate constant. So remember that that rate constant is going to give us the value of K. And the question is, how long will it take for A to decrease? So how long, that means we're looking for the time small t. Decrease from 0.88 molar, that must be my A initial time, to 0.14 molar. That's my A at some later time. So that's just parsing the word problem. Now, because it's first order, we need to use the first order integrated rate law. So this means we're looking for integrated rate law for first order. I'm showing you sort of what it would look like on your equation sheet, where you just get the whole mess of equations and you have to pick the right one. The thing to memorize is that this has to be ln of A versus t is the thing you need to know for first order. So we need to look for the equation with ln of A and t. Now, in this case, you might be drawn to a couple of different equations. I'll sort of try to highlight those. Some people are going to be drawn over here to that equation. Some people also like this one because it has an A and a capital T in it. Note that this one, though, does not have a small t for time in it. This is actually the Arrhenius equation, so no reason to use that one. But again, another good one here would be this one. This is the ratio form. And this third one here is good as well. So all 3 of these underlined red equations are going to be good ones to use, just depending on what you're trying to solve for. In this case, I want to solve for t. So it turns out that pretty much the most efficient way to solve for t is this one down here, the ratio form of the integrated rate law. You can get to t from the other ones, but this is definitely going to be most efficient because everything else is neatly packaged up. So again, our goal is going to be to solve for t. Ln of A over A0 is equal to minus kt. Again, t is what we need to find, so to get t by itself, I'm just going to divide both sides by negative k. That will isolate t and give me ln. Now I can get ready to plug in here. A was 0.14 molar. A0 was 0.88 molar. Negative k, negative 2.1 times 10 to the minus 2 seconds to the minus 1 is equal to t, which when I plug that in is equal to 87.5 seconds. Always check your units again. We have seconds to the minus 1 on the bottom, so we'll get seconds on top. Note that times aren't always in seconds. It depends on the units for the rate constant. Sometimes we have rate constants in minutes or hours, in which case our times will be in those units as well. The ln part has to be unitless, so that one just cancels out here. It can be useful to sort of double check with, again, you could, sometimes you're asked to solve for a bunch of different stuff, so you could use like the half-life as a double check here. 0.88 to 0.14, if I look at that, 0.88, cut in half, 0.44, cut in half again, 0.22, cut in half again, 0.11. So if I look at where I'm looking for 0.14, that's somewhere between 2 and 3 half-lives. Maybe I'm estimating this is at about 2.5 half-lives. This trick doesn't always work so well, but in this case it's pretty good because remember, for first order the half-life is constant. So if I use that half-life equation and get, say, 40 seconds as my half-life, then I have a quick check that this is right. 40, 80 times 2 is about 100. That's pretty close to the 87.5 that I calculated. Lots of ways to check your work and make sure you're giving a reasonable answer in this part of the class. So B, what is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4 seconds to the minus 1? Okay, now this one is maybe a little bit trickier, potentially because it didn't give us the order. So we know the rate constant, so we know the value of K. But there are a couple ways for us to figure out the order. So again, it's a half-life, so we're going to look for one of the half-life equations. I've got 3 to choose from here. These 3. Now, one is to note that we weren't given an initial concentration. Now, the only way we could possibly do this without an initial concentration is this equation right here, because this is the only one that doesn't have concentration in it. And it also will work out because remember that the first order reaction, which this is the first order half-life, is the only one where it's a constant half-life. It's also the one where the units are seconds to the -1. Remember, we looked at the units last time. So if you remember the units on K, that will tell you that this has to be a first order reaction. In this case, a little bit trickier that you sort of had to get the order from context clues here, mainly the units on K and the fact that it's just a constant half-life. It's not a half-life with some initial concentration. With that little maybe trick out of the way, we just plug in T1/2 is equal to ln of 2 divided by K. So I plug in, again, you could just use the constant 0.693, but I'll just use the actual ln, and then I divide by 5.7 times 10 to the -4 seconds to the -1. So my T1/2 is equal to, again, units, seconds to the -1 on the bottom, ln is unitless, so I am in seconds, which is correct for time. When I plug that in, I get 1216 seconds. I only have 2 sig figs here though, so I should round that properly to 1200 seconds as my half-life there. For part C, the half-life of a reaction was 1.7 seconds when the initial concentration was 0.1 molar, but increased to 3.4 seconds when the initial concentration was 0.2 molar. What is the order of the reaction? Okay, so we've got a half-life type equation here. We know the half-life when the concentration is 0.1 molar, and we know it increased to 3.4 when the concentration was 0.2 molar, so this is A naught. This is my T1/2. Okay, first thing we can do is we know the half-life is changing, so we have to rule out this one. It can't be first order. First order is the constant half-life. Now, what about the other one? When the initial concentration is 0.2 molar, it's 3.4 seconds. When it's 0.1, the concentration is 1.7. So this is the case where T1/2 is proportional to A naught. They're directly related. I doubled the concentration and the half-life doubled. The equation that matches that is this one right here, which has A naught on top, which means that this is the 0th order half-life. So this will work. Again, there are some ways you could check it. You could try to solve for K. That would work. I could get that K here is equal to A naught over 2 T1/2. And so I'll get the same value of K. When I plug in, I can plug in 0.2 and 3.4 and 0.1 and 1.7 and get the same value of K. So that would be a way to check this. Another thing you could do is think about it in reverse. Right here, if I think about it the other way, at 0.2, the first half-life, if this was a process versus time, the first half-life would be 3.4. But then once I cut my concentration in half to 1.7, my half-life is now 1.7 seconds. So really, in the course of a reaction, this is the case where half-lives get faster. As concentration of A decreases. So less A, shorter half-life, which is what this equation is expressing. This is just showing that that plugging in for K approach does work. If I solve for K here for the 0th order, I get the exact same value of K for both of these sets of conditions, which is a check that we have the correct order because the rate constant is actually constant. And here is our final example for this set of notes. Okay, so here is the solution. How do we know that the reaction is still first order? It's first order because this plot is linear. So ln of n205 versus time is a nice linear graph. So linear ln a versus t graph is our check. The rate constant k, again, remember, you can either memorize this idea that the slope, when I take the absolute value of it, is always equal to k. That will work. Or again, I can just line up my equation. It is first order. So in that case, it's ln of a is my linear plot. And the equation off that equation sheet that I'm looking at then is ln of a is equal to negative kt plus ln of a0. Again, if I look at y equals mx plus b, even without memorizing that fact, I can quickly identify that negative k is equal to the slope, because that's sort of what lines up in the equation. Then with that, I look at my linear fit here. So negative times m is equal to k. So negative times negative 6.93 times 10 to the negative 3. Now I need a unit on that. My unit here is unitless because anytime I take the ln of something, or e to some power is unitless, so that axis is unitless, this axis is time. Unitless I always represent as 1. So again, my unit here is y over x for my units, so 1 over seconds. So negative times negative, all that did was turn this positive. So I have k is equal to 6.93 times 10 to the minus 3. 1 over seconds is equal to my k here. Just the slope, but make it positive and make the units correct. Half-life, well, this is first order, so just like it's ln of a versus t for my integrated rate law, I also need the half-life equation with ln of a in it. So that's, or not ln of a, but just ln in it. So ln of 2 over k, and that works out to be 0.693 over 6.93 times 10 to the minus third seconds to the minus 1, which works out to be exactly, I think it's 100 seconds when I plug that in. Yep, that's exactly 100 seconds for my T1 half. For D, how much time is required for the reaction to be 75% complete? Couple ways of doing this. Note, we can only do a problem like this where it only gives us the percentages and not any information about concentration when it's first order. Because first order, the concentration initially doesn't matter. It always takes the same amount of time to go from like 100% to 30% or 100% to 1%. Now, the only thing we have to do here then is to account for what that means. So 75% complete means that there's 25% of A remaining. Again, just sort of like a word problem thing here. That's the meaning of 75 complete. And it's how much of the initial starting material that remains that is what we include in our equation. The best equation for this is this integrated rate law, so this one, or sorry, the ratio form of it, A over A naught, is equal to minus kt. Again, we're solving for time here, so 25% of A remaining is what we're looking for. The trick here is that I can just plug in percentages because these are going to cancel out A over A naught. If I use my initial as 100% and my final is 25%, that will work out. I don't need real units there because it'll cancel out anyway. It doesn't matter if those are molar or just percentages. Is equal to negative, again my k was 6.93 times 10 to the minus third, and my units were seconds to the minus 1, times t, just divide both sides by negative k, and that will give me my value of t here. This stuff all cancels, and I get t is equal to. So 200 seconds is a nice round number. In this case, I actually could have taken a shortcut, 25% remaining. If I think about my meaning of half-lives, I started out with A naught at 100%. Half took me to 50%, right? So that's one half-life. The next half-life is going to, by definition, take me down to 25%. And since first order is a constant half-life, this is just two half-lives to get from 100 to 25%. Each half-life is 100 seconds, so exactly 200 seconds just using the half-lives. Now that trick only works if it's 75% complete or 87.5% complete, an integer number of half-lives. Otherwise, you have to use this integrated rate law approach. Again, the summary slide for this set of content is right here. Memorize this linear plot for each order and then just really practice applying the equations. You can look up the equation sheet on D2L or the handout version and just really be familiar with picking the correct equation, plugging in, doing all your algebra correctly. Again, you might need to use some nice algebra here to go from, like, if I have ln of A is equal to 2.34, right? I might need to then say, okay, to get A, I need to take e to the power of both sides and get out of that ln, right? Similarly, if I have an e, I might need to take ln of both sides to get back the other way. Now we are done with experimental kinetics. We have many different ways to figure out the orders of chemical reactions. The next thing we want to do is understand more about those individual details. What are the steps by which a reaction takes place? Because that's going to be how we can control reactions in the lab and catalyze them, speed them up, or slow them down. And that's what we'll look at next when we get at the details of reaction mechanisms.